Welcome everyone. In this video, we'll try to learn about vector algebra and its application. So, let us see why vector algebra is essential. Now, to understand this, let me take a small case where we'll be learning how vector algebra simplifies the difficulty when you go for solution of some real-time problems. And the case that I'm going to explain is one of the case. There are so many cases where you could utilize vector algebra. Now let me take an example of work done, which you would have learned during your physics basic classes. Now there is a block which lies on a horizontal floor, which experienced a force of 10 Newton along the horizontal direction. That is, this is acting along the positive x direction. Now this force is applied for a time. Let me take time is equal to 5 seconds. Now if this force, which is sufficient enough to move the block, if this is greater than the inertia, the block will move for a small distance x. Let me take it as 2 meter. So in 5 seconds the block is moved for 2 meter. So this is my new position. Now what is the work done? According to the formula, work done is force into displacement. So the force that is acting here is 10 and my displacement is 2. So I'll have 20 Newton. Now this is a one-dimensional force. What if my force acts like this? I have an horizontal surface over which I have a body. This experience a force of the same 10 Newton, but instead of acting along the x-axis, here it acts at an angle theta. Now to understand this, you can try doing this activity. Let me take this as your room. You can start from here. Make sure your steps are equal in all the cases that we are going to discuss. Walk maybe 5 steps along this direction. Note where you are. Walk the same spaces of 5 steps along this direction, that is along the other side of the wall. Make a note of where you are. Now, walk along the inclined direction. You can take any angle. Walk along the inclined direction for the same 5 steps. This is 5 steps, this is 5 steps. This is also the 5 steps of equal spaces between each step. Now, if you are here, note it down. You will be somewhere here and here in your respect to both the walls. That is, you wouldn't have covered the same distance you have covered when you are walking in this direction. That is perfect horizontal and this is perfect vertical. This technically means when you are walking along the horizontal or vertical, you are concentrating on that axis alone. Whereas here you are walking covering both the axes. So your total distance is 5, whereas your x and y coordinate changes. This is how even you can find the different coordinates of a circle when you try to create it with the same radius. Now the same way, this 10 Newton will have two components, one along the horizontal, one along the vertical. Now let me take a case where the vertical is not sufficient enough to lift the body, because there you have to go against the gravity. So I have only come here along the horizontal displacement, which is for the same time t is equal to 5 seconds. Let me assume that it is 1 meter. In that case, my work done will become the force F1 into 1, whereas my F1 is this component, not 10. So the value of force that is contributing for the displacement is reduced. So we could use, since this is theta, we could use this as 10 cos theta. I'm not going to take you deep into how we are getting cos theta, but this is the component along the x-axis. Now this is a two-dimensional case where we have converted the force in terms of x-axis alone. That is where the displacement is taking place, and we are finding the work done. What if we go for 3 dimension? Again, the same case where instead of having it along the 1 or 2D, whereas in X and Y, here this is X axis, we have the Y axis here, and this is the Z axis. Now, if there is a force that is acting somewhere here, now the force will make an angle with the Z axis, which is gamma, with the X axis, which is alpha, with the Y axis, that is beta. Now, this is where a three-dimensional force act. Now, again, this could be converted into different components. What is the component of this in x-axis, y-axis, and z-axis? And then find for the force, and you will be eventually adding it. This is a basic case, so the formula is almost what we will do if we don't use vector. But vector reduces the complexity of bringing the steps down to very few steps. Now, again, the work done formula is given by force into displacement. But here, instead of writing the magnitudes alone, that's what I have been doing in the previous cases, magnitude and magnitude of displacement. Now that is here. Now, to understand what is the difference between the vector and a scalar. Now a scalar will talk about the magnitude alone. For example, when I say I am 50 kg, this kg doesn't have a direction. If I stand upright, if I stand inverted, again everywhere I will be having the same weight. So this is your scalar. Whereas your vector has a specific direction. So taking this case, if I tell that I am coming towards your house as 50 kilometer per hour, then I'll be reaching a house very soon if the distance is quite less because I am traveling towards your house. But this towards denotes whether I'm going to reach your house or not. What if I simply say I'm traveling at 50 kilometer per hour and you are waiting in your house, but I would be traveling in the wrong direction? Then I'll never reach your house unless I change my course of direction. So a scalar will have only a magnitude, whereas a vector will have a magnitude and direction. Now, if you have observed, this arrow mark is actually a vector. The line that we draw represents the magnitude. This represents the magnitude, and the arrow mark represents the direction. So this represents the direction. So the line and an arrow mark together, that represents a vector. Now we are going to use the vector approach to find the work done. So a vector is represented as x component, and these represents here I, j, k represents here respective axis. So this is xi plus yj plus zk. This is your force. The same way, my displacement can be found with the help of x1i plus y1j plus z1k. So these are the vectors for force and displacement. If I directly substitute them here and multiply, this is called as a dot product, which we eventually learn in the later stage because we are only trying to understand the use of a vector. So by multiplying these two vectors, we will directly end up with the work done. Eventually that will be a scalar here. So this is one of the way where you could utilize vector algebra or vector approach to solve problem. So particularly a three-dimensional approach. Whenever you have a three-dimensional condition problem, vector algebra plays a crucial part because that reduces the complexity in doing more than 4 or 5 steps. It reduces it, bring it down to few limited steps because we apply vector algebra. So this is the use of learning vector algebra. Now, with this, we'll see what is a vector, which has been already discussed. A vector has both magnitude and direction, which is represented by a line with an arrow mark. Now, there are different types of vector. For example, a zero vector or a null vector, which doesn't have a magnitude because it is zero. Then we have a unit vector. So a unit vector is something that has magnitude as 1. Magnitude is equal to 1. So this unit vector plays again a crucial part. In case I want to convert a scalar into a vector, because a scalar has magnitude but doesn't have a direction. So if I give you a specific direction by converting that into a vector, so that direction can be given with the help of a unit vector. So this unit vector, since the magnitude is 1, which is a multiplicative identity that doesn't affect the magnitude if you multiply it with some other value, this is a direction giving vector. So this will give you a direction. So a scalar can be converted into a vector with the help of a unit vector. The next one is a collinear vector. So the collinear vector is a vector which acts parallel to the same line. For example, if I have a straight line like this, if there is one vector here, the other vector here, the other vector here, they are acting parallel to the same line, or these three are having the same line of action, parallel line of action, then they are called as collinear vector. Co-initial vector. So from the name itself, they originate from the same point. They will travel a different direction, but they will originate from the same point. So these are co-initial vector. Then you have negative of a vector, which is very, very essential or very, very useful when you try to subtract two vectors. For example, if this is 10 Newton in this direction, the negative of this vector will be exactly along the same line, but it is in the opposite direction. You can relate it to Newton's third law, action and reaction. So the action acts along the right hand side, the reaction goes towards the left hand side. So this is a negative of a vector. So this is the introduction, right? So why we learn vector algebra, what is the use of it, and what are the basic types of a vector. So with this, you will be able to identify. Now, since you know the practical case, when a question is posed to you, you can identify whether that is a scalar or a vector. Because if the value that is asked to you has a specific direction, or it will be defined only if you define the direction. For example, a force. A force needs a direction, not only the magnitude. That is a vector. Now we have work done. So I have done some work, right? In what direction, that doesn't matter. So this is a scalar. So if the direction defines you fully, then that could be a vector. Whereas if the magnitude alone is enough, then it is a scalar. So by this, you would be in a position to identify who is a vector and who is a scalar. So we'll be trying to do some sums in the upcoming videos. Thank you. Happy learning.